All right, so we're going to get started. I am so excited to welcome our guest speaker today, Karissa McKelvey. I've known Karissa since I was a grad student at Indiana University and she was an undergrad there. Karissa studied computer science. She went on to briefly work at Google until she decided that the corporate world was not for her, and moved on to working in a lot of interesting nonprofit tech organizations. And most recently, she's been involved with an organization called Digital Democracy and the DAT Project. And today she's going to talk about a topic that I'm very excited about that she's bringing to us because although peer-to-peer networking and peer-to-peer applications are an important example of distributed systems, they haven't really been our main focus in this class. So Chris is going to be telling us about peer-to-peer applications, and she's given this talk to peer-to-peer application developers, and I don't know if she's ever given it in a school setting before. So it's really exciting. There's going to be a lot of practical advice. And I'm happy to welcome Karissa. Take it away, Karissa.
Thanks, Lindsay. Yeah, the corporate world was not for me. So I'm also going to give you a bit of a why I decided to start working on peer-to-peer applications and what was exciting to me about them. I'll also get into a little bit of the history of peer-to-peer and then how you can get involved. So I'll be giving you a bunch of links to things you can follow up on during the summer. It's all open source, all things I'm working on, so you can get your hands dirty and play with it. I'd first like to talk, just, sit for a minute. And I know for me, it was like a little bit weird to come on a, Wednesday morning and talk about peer-to-peer applications and building them today, just because of everything that's going on in the world. And it's been hard for a lot of folks to, just get up in the morning and go to work. So or go to school. So I want to just acknowledge all the pain and injustices that's happening in the world, and especially in this country. It's been happening for centuries, and just sit with that for a minute before we get into, talking about this stuff. I hope that today and this week and this weekend we can start seeing changes and see things get better for everyone who's feeling this pain. I'd like to, just start talking a little bit about myself and what I've been doing the past few years. I've been working on DAT, which is a peer-to-peer protocol. I started working on this in 2014. We were first focused on scientific use cases. And I've also been working as a board member for Code for Science and Society. It was the first nonprofit I co-founded to incubate DAT in the nonprofit world about 3 years after it was developed. Starting a nonprofit is not easy. The two executive directors that are currently running it, Joe Hand and Danielle Robinson, are amazing. And they incubate a lot of amazing open source projects for the public benefit. I also work with Digital Democracy. That's my current main squeeze. We work on peer-to-peer applications. We've been building this particular peer-to-peer application called Mapeo, which I will talk about today. Indigenous people in Peru, Ecuador, and Guyana were co-designing this with us over the past 5 years. So they use this application offline to collaboratively edit maps. So as you know, you've been talking for a long time about how time is an illusion, and conflict resolution and CRDTs, or maybe you haven't, but I think that there's basically a lot of need for this kind of stuff, when you don't have the internet, you have all these devices in the field that need to edit and share data with each other. And so peer-to-peer for these indigenous communities that are protecting their lands and their heritages, this is a super important part of what they're doing. They can share and synchronize data offline without a centralized server, just using all the devices they have. So for them, peer-to-peer isn't just like a cool idea, it's like an actual necessity of getting the work done. And I can talk a little bit more about how we do it. I've also been helping out with this project called Peer Maps, which is like OpenStreetMap or Google Maps, but it's entirely peer-to-peer. And today I'm going to talk a little bit about the why, what, who, how, and when of peer-to-peer applications. When I get into the how, I'm also going to talk a little bit about these 4 principles that I think are funny, but also pretty true about peer-to-peer. You've already talked a lot about how time is an illusion. I'll talk a little bit more about that as well. Data is a virus, connection is optional, and safety is a circle. I'm excited to bring this conversation in. I've done variations of this talk over the past few years, but I've been working on a new workshop and handbook for building peer-to-peer applications for people like yourselves who are interested in distributed systems. Yeah, that kind of thing is part of my side project this year, and I'm excited to share a little bit about what I've been thinking about.
Karissa, where can we find that workshop and handbook when it becomes available?
You can follow me on Twitter, but it's going to be on decentpatterns.xyz. I will also share this this like PDF, so it has all the links in it.
Thanks.
Mm-hmm. So let's talk about why I got into peer-to-peer. Let's play a game. I know it's the morning, so figured I'd start with a little game. So we're gonna talk about the prisoner's dilemma. I wonder if anyone's heard of the prisoner's dilemma. I'm just getting like a gauge. I know it's really weird over Zoom, but I don't know if I don't know how to do this. I guess I could just go over it really briefly.
Yeah, I think we're getting some positive responses in chat here.
Okay, great. Cool. So essentially, if you remain silent and the other person confesses, the person who confesses gets to go out free, and the other person has to go into jail for 20 years. Say if you both confess, you both go into jail for 5 years. Say the other one did it. But if you both remain silent and you have some mutual cooperation, then you both get only 1 year each while you're being interrogated in prison. So this is classically known as a prisoner's dilemma. The optimal strategy that you should do is to remain silent. So you talk about it ahead of time. You're like, okay, don't narc on the other person. And then you'll both have fewer years of jail to go total together. But what actually happens is someone ends up confessing and more jail happens for either both of you or one of you. So this is one of the games that we can play in game theory and economics. Garrett Hardin called this a tragedy of the commons, where freedom in a commons brings ruin to all. So the idea is that people are rational actors that are going to act in their self-interest and ruin everything for everyone. I'm paraphrasing, obviously, because it's a peer-to-peer class. I'm not trying to get too deep into this, but this is the central idea. But you can see this characterization happen in fisheries, where people overfish, and then you don't have as much fish for other people. You've seen this in pastures. And the dominant strategy for preventing this from happening is to, the people have employed, especially kings have employed over the centuries, is to create fences. So they enclose these pieces of land or parts of common ownership and give it to a private owner. So you have a fence that covers the land, and then that person is now in charge of making sure that that piece of land or that resource is used. So this has been a strategy that's been used for centuries to prevent this problem from happening. At IU, Eleanor Ostrom, she actually came up with a framework for preventing the tragedy of the commons. She won a Nobel Prize for it as well. She was the first woman in economics to win a Nobel Prize for this.
IU, by the way, is Indiana University, where I went to grad school and Karissa went to undergrad.
That's right. Sorry about that. IU. So she talks about mutual cooperation and how people aren't always acting as rational actors. We can think of them instead as some sort of irrational managers. It's kind of my characterization of the concept. But that mutual cooperation is possible if we manage it together cooperatively. She talks about this in Governing the Commons. You can learn more about it. Came out in 1990. She pulls from her framework together from studying, using mixed methods from all over the world, Nepal, here's her in Africa. Her work was pretty foundational in economics, but what does this have to do with the internet? Oh, my Zoom is, where am I? There we go. What does this have to do with the internet? Right, so we're talking about, oh man, no, okay, cool. Sorry. What does this have to do with the internet? So the internet, we could think of it as a commons. It's a big pot of knowledge, right? And in 2011, Eleanor Ostrom actually came up with a book with Charlotte Hess, came up with a book for this. So they wrote a book about how we can understand knowledge commons. This was one of the last books she published before she died. So when we think about knowledge on the internet, what are we thinking? We're thinking libraries, scientific articles, wikis, maps, online classes. We're in one right now. And essentially, this digital knowledge is owned by people who create it. But in practice, we need to look at, how we see knowledge as a commons. It's a shared resource, but if we look at it this way, we can see what are its possibilities, but also what threatens it. So what threatens digital knowledge today? You guys have any ideas? Thinking about knowledge on the internet, what are the big threats that we see?
In chat, copyright and patent law are being mentioned. Misinformation, DRM.
Awesome. Yeah.
Fake info.
That's right.
I would say centralization, but I'm probably jumping ahead a little.
So we're treating digital knowledge as, in a similar way as we've treated pastures, right? So we've created literally fences around this knowledge. The knowledge that you post on Twitter is controlled and owned by Twitter. The knowledge you post on Facebook is controlled and owned by Facebook. And now we're faced with a situation where we have to basically lobby and plead and try and convince these corporations or these private owners to do something about all this. So we don't have a collective ownership of the data, essentially. One particular case that I think is particularly relevant to academia is scholarly publishers. So Elsevier is one of the biggest scholarly publishers in the world. They control and own a lot, and they have a centralized service that controls and owns a lot of the scientific articles. And so despite, the problems with copyright and DRM, which are serious and problematic, I'm not a lawyer, so I'm not going to be able to talk about that. But I think that it is related in a lot of ways, or we don't have a good way or a sense of, we don't have a really good framework for how digital knowledge has evolved from, 100 years ago. One of these is that, these scholarly publishers, they have these centralized services, and they're like, oh, well, it costs us money. It costs us a lot of money it's a proprietary service. It's very expensive to maintain. we need to charge people money to access this information. So what ends up happening is the public pays twice for this data. So they're paying to create the knowledge that then they have to pay again to access. And this comes from an antiquated idea that, I think it comes from, the idea that paper is also difficult to create, but I think it also comes from this idea of like private ownership and commons. It also has other issues like the 404 problem. So if it's a centralized service using HTTP, you access it one day and the link's there, you access it the next. They've just changed the link and you don't have access to it anymore. So this is one of the problems that we were really focused on tackling with DAT in the initial couple of years. We also have to contend with other more sinister kinds of attacks on digital knowledge that maybe aren't necessarily attributed to a single person. I know I have Mark Zuckerberg here, but Google's also been part of this. So once you have a single entity that is in control of data, they can do things and collaborate with governments that would like to filter sites, or the 404 problem becomes actually a censorship problem and expands from there. This is in 2018, but this is just the beginning, basically. There's censored search is just one of the things that we can predict will happen related to digital knowledge and accessing it around the world. So these are the kinds of things that got me excited about peer-to-peer and thinking about other ways that we can manage our knowledge collaboratively and collectively. So when we talk about threats to digital knowledge, threat models is like a common, heady term used in design world about how do we model what our threats are and how do we figure out how we want to design our systems so that they aren't so susceptible to those threats. Other kinds of threats you can imagine for data are also like earthquakes. If I have a data center, earthquake goes down, and now the data center is down, I want to have a copy of that data somewhere else. So this is the kind of concept, this is the framework that you could think about the distributed systems, but you could also think about it in other ways. But I want to kind of move this from threat models to trust models. So in peer-to-peer, we're talking about threats, but we're also talking about trust. Because we can't trust every single computer that has the data. So in a typical distributed system, if you're working at a large company, you might have, you can actually own and control most of the computers or all of the computers that you're putting your data on. With peer-to-peer, you don't have that luxury. Someone could be at a coffee shop that you're sharing information with. You could, there's lots of different ways that you can model trust. If you're going to be, I'm going to talk a little bit more about this in the later part of this, but I think it's just important to visualize and think, okay, who am I trusting with my data? With peer-to-peer, I have to be very careful with it. So let's talk a little bit about what peer-to-peer is. Are there any questions so far?
Oh, I just want to point out how important a point it is that you just made. So far in this course, we haven't spent a lot of time talking about this question of trust, right? We talked about MapReduce, right, which entirely runs in a Google data center. We talked about Dynamo, which entirely runs on Amazon servers. And the key value store that you're implementing, you're assuming that all the participants are trusted, right? So in all of those settings, there's an assumption of trust among all the participants. When we talked about consensus protocols, we weren't dealing with Byzantine faults, so we were assuming that nobody was going to start intentionally sending misinformation, right? Intentionally or unintentionally start sending misinformation to other processes. That wasn't part of our fault model. So if you thought programming distributed systems was hard before, think about doing it in a setting where you can't even trust all the participants, and that is what Karissa is talking about. So this is really interesting.
Thanks, Lindsay. So let's talk about what what are we talking about? Wait, what? Peer-to-peer? So peer-to-peer has people usually think about distributed systems or peer-to-peer. They think about this. They're like, oh, it's a distributed network, or it's like a peer, like everyone connects to everyone and we're all like connected and it's like all horizontal, yay, blah, blah, blah. But in practice, it's actually a little bit more like this. There are some nodes, some computers that are more privileged than others, whether it's because they're running on a VPS and they have, IPv6 and they're not behind, a restrictive middle box or router, and so they can connect to anyone. There's, maybe you want to back up your data when you're offline into a cloud service. And so most people actually get your data not from your computer, but from the cloud service that you set up. So there's lots of, there's lots of different types of topologies, you could say, in peer-to-peer networks. So although people usually they'll say, oh, we want it to be like this, even if they're saying that, it's actually looking like this. There are some nodes that are passing through a lot of the information. So when we talk about trust models, we're also talking about how are we trusting these intermediaries, these centralized servers that are essentially passing data from peers, one peer to another peer. One classic example of this is Usenet. In 1979, this is the mother of peer-to-peer, right? It's a relatively unstructured peer-to-peer network where you have servers that literally just pass all the information all the time to every other person, every other server. And eventually all the information will reach everyone. So it's actually really great. It still works. People still use it, even though it's pretty simple. Then you might have heard of Napster, 1999, and BitTorrent, which made peer-to-peer famous. It actually started making peer-to-peer synonymous with copyright infringement, right? Or pirating. So what made Napster and BitTorrent faster and better at finding data is they introduced a more structured model of how you can access data. They introduce more centralized servers that are more acting as bootstrap servers or peer introductory servers, essentially. I'll talk a little bit about this later. But the concept is that they're more structured in the way that they work.
So by the way, I'm curious if there's anybody here other than me who has used Napster. Anybody else who's old?
I used it, but
did you?
I didn't know what I was doing.
All right. All right, a few people are reporting in that they are old. Okay, go on.
Awesome. So BitTorrent, it's peer-to-peer. It's massively adopted because it's very simple. It's not as simple as Usenet, but like you were hearing from the other guest lecture last week, the simpler you have things, the easier it is to actually build on them. The more complex, things that you add to it actually makes it more difficult to build, maintain, and deploy in real-world scenarios. So BitTorrent's specialty is just how doggone simple it is. One of those simplistic decisions they made is it only works for static files. This is something that we wanted to change. And when we're talking about building peer-to-peer applications, if you want to build a peer-to-peer social media or a peer-to-peer web browser or a peer-to-peer collaborative map editor, you actually need to be able to edit data, right? So BitTorrent made this simplistic decision, but we can do better. It also scales pretty poorly on really big data. And links can be sniffed by third parties. I'll talk a little bit more about this when I get into exactly how we were able to overcome this. But essentially, anyone who had the original content or anyone who has the original content that they're sharing is able to, share it on the network and then figure out everyone else who has that same piece of content. This makes it really great for some things, which is that it's really easy to find other people who have the same content as you. But it also means that anyone who has the same content can figure out who's sharing it, which is what caused a lot of people to get in trouble for using it. So yeah, today, what are we doing? So with BitTorrent and Napster, I said they're using very structured networks. Now people are moving more towards hybrid models, they call it. But essentially, picking and choosing what is necessary for whatever their use case they have. So who are these people that are doing this? I'm going to talk about 3 particular use cases. I like to start from the users. I mean, we can talk about theory first, but you know, there's pros and cons to doing that. I personally like talking about users first, and help contextualize what we're actually doing and what the boundaries are for these applications. So with decentralized data preservation, it's very similar to distributed systems typically, right? You want to keep data online. There's an earthquake or censorship scenario. You want to make sure that data is still available. So in 2005, Stanford came out with locks. Lots of copies keep stuff safe. Very cute name. It's one of the longest running peer-to-peer digital preservation systems. It has some very novel ideas of opinion polls, but I don't think that's like the most interesting part about this design. The most interesting part about locks, I think, is how they restrict which content is basically on the network. So there is an alliance and a council that decide, you know, what data actually goes into the digital preservation system. So this creates boundaries around the resource. When we're talking about managing a common resource, you have to decide which things are going to be part of this, you know, common pool resource, this resource that we're all managing together. And this is what they're able to nail really well is say, this is a digital preservation system. We're going to use it for scientific articles. I'm not going to go too deep into Ostrom's principles because this is about peer-to-peer applications, but I really recommend looking at this and, you know, taking some summer reading. One of the biggest things, our users are clearly defined and the community manage these rules. And I think Locks does this really well. One example of this you could say is like, say there are many institutions that are opting into replicating these articles and being part of the peer-to-peer network and basically donating their data centers to the network. They have a monitoring system. You can see who is, you know, having a hard time hosting its data, for example. So having like real-time monitoring is also part of this. We call this in some ways the health of a data set. So this design pattern is essentially you want to make sure there's at least 2 copies available of any data at any time. Lots of copies keep stuff safe. It wouldn't really make sense if there was only one person seeding that information or sharing that information on the network. So you want to make sure that there's multiple people or multiple copies of it on the network. So having an insight into this is one of the key pieces of the data preservation and something that we're trying to surface as part of our apps in peer-to-peer apps when we build them is showing users literally there are 2 other, you know, copies of this on the network, and then being able to show them, oh, there are 3 now, so that they can make sure that there's many copies on the network, and they know that the health of their data. One, you know, thing that would be really common to happen is if you have a laptop and you're the only person hosting it, and you turn off your laptop and go for a swim, you know, now no one can get access to your data. So this is a key part of the health.
I'm really glad, Karissa, that you brought this up.
Yeah.
So this is something, this concept of making multiple copies of things has come up multiple times in this class, right? So we talked about how you can get fault tolerance by having multiple copies. So for instance, if you want to make sure that a message is received, you should send it more than once. And if you want to make sure that your data survives a crash, then you should have multiple replicas of it. And if you want to make sure that that a computation is fault tolerant, then you should allow for there to be redundant recomputation. This, and I had not heard of this lock system previously. I'm not familiar with the data preservation literature, but I'm so glad that you brought it up. I love the name.
Yeah,
and because it's perfectly in line with this concept that we've been discussing all through class, that a fault tolerance often involves making copies. I want to mention also that there's a flip side to this, which Denise Altenbogen at Google talked to my class about last year, which is that if you want to get rid of something, like let's say that you're trying to um, comply with legal restrictions on how long to save user data, if that user data is replicated, then sometimes it can actually be very hard to get rid of all the copies of it that you have. So she was telling me that at Google, it was actually a challenge to comply with GDPR for some of their replicated systems, which were designed to be fault tolerant and preserve data, even in the event of failure, which I thought was really interesting. So being able to support both of those situations, how do you make sure that the data is already there, always there when you need it? And also, how do you make sure that it's really gone when you need it to be gone?
Yeah, exactly. That goes to my second point of data is a virus, right?
Mm-hmm.
I mean, it's kind of, I came up with this concept like before the COVID virus, but the concept being just like, you can pass data to other people or other machines, but it's actually really difficult to rein that in once
Mm-hmm.
it's that's part of the protocol
Mm-hmm.
of what you're doing. Yeah, so I was really inspired to look at the original ARPANET and think about, wow, like this concept is not new. People have been thinking about this for 50, 70 years of it's not surprising that universities would be the place where peer-to-peer systems would be experimented with, because that's where the internet was also originally experimented with. And, you know, see Michigan, CMU, and other places, UCLA and other places here that are hosting these early prototypes of the internet. And we see the same thing happening again. Community mapping, this is what I've been working on the past few years, 3 years now, the digital democracy. So we have this local first map editor, we call it local first. I'll add a link to later so you can read up. There's a really nice paper about that defines local first called Mapeo. We work in solidarity with indigenous communities and frontline communities, marginalized communities around the world, and co-design our tools with them. We have decades of experience working in the field. So essentially, people take their phones. We have an application, a phone app that they use to take a photo and write some information about the oil spill, or a tree, particular type of tree, or animal tracks, or a mining operation. We call this environmental monitoring and human rights, kind of like a human rights watch. So when they take this information, they go out for like 3 to 5 days with like battery packs and solar power, and they take their phones and they do this, and they go for these long walks. So they're doing this all offline. There's no satellite internet. There's no 3G. So when they go and they edit information and add information, when they come back to the central point, wherever it is, the community center, they need to be able to synchronize that information with other devices, because there's no internet, even in the community center or even the closest town. If there is internet, it's like very slow and shared. It's like one 3G connection shared with like, 4,000 people. So you can't really expect them to be able to share, high resolution images over this, 100 high resolution images over this. It makes a lot more sense for them to be able to share from the devices themselves to each other over the local area network. This is not a new concept, but historically people have either used paper and pencil to do this, or they simply have their phone and they take photos of this, and then they have to go 12 hours on a canoe to like the fastest internet that they can get to order to upload all of their information onto the internet, or to someone like a legal advocate. So it's a very complicated process. And our goal with this was to make this a lot easier for people and have them be able to own their data. Another relating back to the health discussion, if you notice, this is like actually the jungle. So this is the Amazon rainforest. Devices get dropped in the river, or it starts raining all the time. So being able to synchronize devices and actually use the devices around them as a way to keep stuff safe and have copies offline is super important to be able to preserve that information in this kind of environment. So this is the example of like kind of the kinds of pictures they might take, looking at you know, real oil spills that are affecting people in their communities. We take the OpenStreetMap interface. This is what it actually looks like. It's very simple. People can create a point, a line, or an area, and edit that information, and then synchronize with other people. So you might be thinking, oh, editing and then synchronizing. Yeah, we have basically a CRDT under the hood. We do some conflict resolution, which I'll get into a little bit later. This is them with their maps. This is, oh, I forgot to put, I think this is in Ecuador. Yeah, this is the Waorani people. Okay, this is my keynote's like really slow. I don't know why. Are there any questions about that? I think before I get into the next.
There was one question shared in chat. So the question was, what role do you think anonymity plays in data sharing? Do we need to combine things like Tor into the model?
It's a good question. Yeah, I'm going to talk, basically the concept that I come up with is safety is a circle. Mm-hmm. I'm going to talk a little bit about that, but I think there's lots of, Tor is one option. The issue with Tor is that it makes things really slow. So you have to be really careful about when you're using it, making sure that it's like actually really needed. Another way you can go about it is to set up a centralized server that people trust. And this server might know the IP addresses of the people involved. But you know, having some way to prevent that. There's also, this is like basically an area of research. There's a protocol called I2P that is trying to improve on Tor, and you know, ways to do this. It's definitely not a straightforward question.
Thanks.
People using this for social media. There's a web browser called Beaker you can check out. Secure Scuttlebutt is a social media app that is peer-to-peer, and Cabal, which is a chat program like Slack that you can use today. So how are we doing all this? This is I'm going to touch a little bit on the how of time is an illusion, data is a virus. So let's talk a little bit about time. I'm not going to go too far into this because you already kind of probably know about this. You've covered a lot in class. I actually was really inspired by this from a couple of days ago that Lindsay shared. I really liked this quote. It's like this migrating birds quote, like a scene so vast that can't captured by a single photograph. So we have to define meaningful and then determine how all those photographs should be taken. I really like this because this is how I feel like what I do all the time is like, think about the user experience. What is a meaningful notion of time for the user? So you can theoretically think about what's going to happen, but at the end of the day, if the user thinks that it's wrong, the user thinks that it's wrong, and the user is always right. So we have to think about how we design our architecture based upon the user experience that the user wants to see. And this is how I craft conflict resolution mechanisms. So, yeah.
Yeah, this is reminding me a little bit of how, last summer I had the opportunity to go and talk with some people at Blizzard Entertainment about distributed systems. And so they build massively multiplayer online games. And for them, it's all about making the player experience good, right? And they have to contend with all the problems of distributed systems that everybody else has to. But they foremost in their mind is making it fun for players. And so they have all kinds of tricks that they can play to try to make it fun, right? You know, you can try to predict what's going to happen, and then show the player something, and then roll that back if necessary. If something is going to take a long time to synchronize across the network, then there can be some really long animation where, you know, hopefully by the end of the animation, the synchronization will have gotten done. Stuff like that, which is so games are, there's this interesting example of like the situation where just like in any other distributed system, there's latency that has to be hidden, and they have to try to hide it in a way that that actually makes things fun for the user, which is this really fascinating and complicated HCI problem. And I am inspired by what they do.
Yeah, that's super interesting. Yeah, I remember playing games, and when my internet was like 56K and everyone else was using like faster internet, I remember being like, oh, like you can see someone like moving forward, and then like the character moves back, and then they move forward, and then their character moves back, and it's like, oh, like, yeah, the computer is trying to guess, you know, what's going to happen.
Yep.
In practice, in a lot of the apps that I use, we don't do a lot of guessing, but we do. I mean, I guess in some ways we do. Say like two people edit the same thing offline from each other and then synchronize back up. One might say, "Oh, I deleted this," and the other one said, "Oh, I edited it and added, you know, fixed a typo." So like, how do you reconcile between someone deleting something and someone editing it, right? This is like a problem we're experiencing currently.
This is like this problem that you just described. Like one person deletes a thing while the other person edits it. This is like an active area of research to decide what to do in that exact situation.
Yeah, and it depends. Like, I feel, you know, there's at least from a practical perspective, we come from the situation of like, okay, we just try and guess. But I think there's a lot of reasoning to actually show the user and say, this other device deleted this. What do you want to do?
Yeah, sometimes the right option is to just kick it back to the user and say that let the user, because you have to, at some point you have to acknowledge the fact that whatever merge strategy you come up with is not going to be as smart as the humans.
Yeah, exactly. Yeah, and I think it's also a responsibility and a consent thing for users. So we want to have users have consent over what the application does with their data, and what's going to happen next. And it can be really jarring to like just all of a sudden all your data is deleted and you don't know, why. So having clear, after a synchronization happens with another peer, having like a clear, even if it's just saying this user deleted 300 items, like that is a useful thing. And also having history and be able to roll back and that kind of stuff from a deletion. But yeah, these are all extra features that honestly a lot of peer-to-peer applications in practice don't implement or don't have. And I don't think it's because they don't want to implement it. It's just such an edge use case that a lot of times people are like, that might happen once in the next year to one person. So in that case, we will come up with a guess or help them with it. But if you're actually going to roll this out to 1 billion users, then it's going to happen more often than that. So I think for many applications, although it's low on the priority list, I think it's very crucial for mass user adoption. Any more points on that? I'm going to move on. Questions, comments?
Go ahead and move on.
Cool. So with DAT, I'm going to talk a little bit about some of the underlying primitives of DAT, which are used in all these applications I've been discussing. We wanted to really make sure there was no eavesdropping by default on the network. When you're building a peer-to-peer application, say you have this peer-to-peer Slack or peer-to-peer file sharing tool, and you're trying to collaborate with other people in a team or in a set of 30 people even. You don't want some random person on the internet just because they have some PDF that you uploaded it to be able to see that all 30 of you have that. So for a practical use case in a peer-to-peer application, we wanted to make sure there was no eavesdropping. So I'm going to talk a little bit about how our data structure works that we build all these applications on top of. So we use append-only logs. So append-only log, essentially you add items to the list. We use append-only logs. So, we use append-only logs because then we know that data is not going to be tampered with. We need to be able to see the history of data. So you've probably covered this a lot, so I'm not going to dive too deep into it. But how can we share append-only logs with other people in like an application? Where we don't necessarily trust everyone who could maybe get access to this information. So we use Merkle trees. So to review Merkle tree quickly, you add some data. We have this thing called sequence numbers. So add data sequence number 0, and you create a hash from it. And this creates a root hash. When you continue to add data to the log, so the log is going from left to right the time, then you hash it again, create the root hash, keep adding data, the root hash. So the root hash is actually changing every time you add data, right? So with BitTorrent, when you add a file, it creates all of these data points and then creates a root hash so that you know the file was never tampered with and anyone can serve any piece of the data to anyone else because you can verify. The root hash verifies that all the data is correct underneath of it. So say Alice wants to share the second sequence number 2 with Bob. So say Alice shares the root hash with Bob. So Bob's like, okay, I trust that this hash is right. And Alice wants to share this number 2. Alice needs to share hash number 6 and hash number 1. And we're able to rebuild the tree. We don't actually need data points 0, 1, and 3, right? So Bob can check that these hashes match. So this is much more efficient because we only need to send log n hashes. We don't have to send every single hash in the tree. We only have to send 6 and 1, and Bob can reconstruct the tree to make sure that the hashes match. So how do you do this in real time? So like I said before, the problem with BitTorrent is that static files aren't very useful in an actual application. Because every time we append data, the root hash changes. So how can we keep track of this root hash? So we're going to use cryptography for this. We generate a key pair. So every user in the network has their own secret key and their public key. So say Bob trusts Alice's public key for some reason. Maybe Alice shared the public key on Signal or, shared it in a file somewhere in some secure way. So Bob trusts that this public key is actually representing Alice. So when Alice takes her secret key, she has her secret key on her computer, her device, or she never actually shares that secret key publicly. It's very important to keep it secret because anyone who has it can add data. She signs the root hash. And then when she adds data, she signs the new root hash. So then Bob can use the public key to verify these signatures over time and make sure that Alice is the one who's writing to the log. This is called HyperCore. It's been in design and development stages since 2014. And it's pretty stable at this point. It's being used in Mapeo, in Cabal, in Beaker, and in a lot of other applications. We have about 20 organizations that are using us right now and growing. It's a Node.js application, but there is a REST implementation currently in process. So say you wanted to do a file sharing tool. Actually, maybe I should ask, is there any questions before I move on about HyperCore?
Not yet.
Okay, cool. So how do we turn append-only logs into a file sharing tool? So you take a file and you cut it into pieces. And then you have your data. So you insert each piece into the log. This is very similar to what BitTorrent does. We also have, in this file sharing tool, DAT, also called Hyperdrive, we insert we have a separate log for the file name and the file metadata. So you can take a look at that as well. I'm not going to go too deep into Hyperdrive today, but just give you a sense of how you might do this. You could also think about different types of applications, right? So this is about a file, but you know, these datums could be anything, right? I could add a JSON blob or a protobuffer. I could add any kind of data in there, which is kind of cool because you can think about many different kinds of applications that could be used. In Mapeo, we encode all of the information about a particular point on the map using OpenStreetMap's specification between node, ways, and elements. So we're actually encoding data inside here, inside each piece of the log. So this is outlined in our paper, which came out in 2017. So we'll talk a little bit more about Mapeo and how we take this from, okay, I'm simply sharing data to I'm actually collaborating on a map, which is very next level. So say all these people have their devices. Each one of them has a laptop or a phone. Each one of them has a public key and a secret key assigned to their Mapeo instance. So you can imagine in this network, you have a public key and a log, many public keys and many logs. So how do if I want to get access to a particular map, say there's, hundreds of communities that are using Mapeo in practice, I don't actually want to get everyone's public key and everyone's log of all the people who've ever used Mapeo, because that would be very slow. But it's also like someone was mentioning before, and on like a privacy issue, I actually don't want to have everyone's data, even if it's encrypted, because I'll still get their IP address potentially, or maybe some metadata information, or maybe I'll be able to decrypt it because they posted their secret key on accident. So I think it's very it's very dangerous to like try and replicate everyone's public key all the time, even if it's like you have a theoretical model for technically how it could work. In practice, when you actually implement these things, bugs happen. So one way we try to mitigate potential for data leakage is to only replicate with other public keys and other logs that are within your project. So literally people that you've decided that you want to collaborate together on. This is really not that dissimilar. This is very similar to how centralized services work, right? Like if you have a Slack channel, you know who has access to the Slack channel, right? Like you don't have random people. You might have Slack looking into who's in what channels or whatever, but you're not going to have random other people in random other Slacks knowing who you are. So let's go back to the concept of the log, so the hypercore. So see these data at the bottom? Now I'm just like putting them on top. So kind of removing the verification part and assuming that it's there, but we're going to just focus on the data because this is where things get a little more interesting and experimental. So see, each person has their log and their data. We want to be able to share that information with each other. So Alice shares all of her logs to Bob, and Bob shares all of his logs to Alice. And locally, you create a database over those logs. Essentially, you're in this database, you're running over the logs and basically going over each log and saying, hey, like what's in this log? Okay, Bob updated something. Okay, I'm going to update the database. You actually have a process that's running as a database to actually say, hey, I'm trying to make some meaning out of these logs that people are posting. So this is kind of in an abstract how we're, the model for we're going for. This is sometimes called Kappa architecture. I'm going to post a workshop at the end of this called KappaDB that you can go through. It's in JavaScript, but it's a practical hands-on workshop that you can use to build a database like this. So just a reminder, like these logs are the hashes. So when we talk about data as a virus, like if you're looking at these logs, like you might imagine, oh yeah, of course, data is a virus, because like I can, and we talked about this before, so I can skip a little bit ahead, but everyone has copies of everybody else's data. So that means if someone edits something and only wants to share it with Alice, if Alice is also part of the project, then, I mean, if other people are part of the project, even if you only shared with Alice, Alice could share it with other people. So yeah, you can't just assume that your data is only going to go one place. So when we edit data, how does that actually look? So say Bob adds a new data point. You actually create, what we do is we create links back to other data. So say Bob is going to edit one of Alice's data. Say he's we could actually maybe go to a whiteboard here, because I think probably explain this better on a whiteboard.
Sure.
Yeah. This is like the newer slides that, whoop. Whoa, how do I stop? Okay. All right, cool. Make sure, see. Yeah, okay.
Looks like we're having some technical difficulties and we just lost Karissa. So hopefully she will rejoin momentarily. If we don't get Karissa back, so there's only 7 more minutes or so of class. If we don't get her back, we may have to wrap up early. But in the meantime, does anybody have questions about any of the stuff that Karissa was discussing? So I thought it was great to see Merkle trees make a reappearance. We've now talked about them a few times. So it was interesting to see them come up both in the context of Dynamo and then in the context of the blockchain discussion and now here as well. Karissa's take on it is a little bit different from what we were discussing, because we weren't thinking about necessarily this question of do you trust that this data from this other person is correct. We were only using them in the context of saving bandwidth between participants. So there's an interesting question in chat is, okay, is the virus in data is a virus just saying that data can be spread quickly, or does it mean data can be harmful? Well, data could be helpful or harmful, right? Just like any other tool. So I think, yeah, I think you would have to ask Karissa exactly what her intent was with that statement. Hopefully we'll get her back and we'll be able to get an answer for her from that question. Let me see if I can get a hold of her. I think she's rejoining. I think she'll be back on stream momentarily. Well, it looked like she was rejoining, but I only have a blank screen from her here on the stream. Yep, we lost her again. All right. We'll see if she returns. In the meantime, as long as we're here, I want to take care of a couple of items of course business. So in case folks didn't see it, I shared a document which was a gigantic list of questions that you can use to study for the final exam. So I shared that in the announcements stream on Slack, on our course Slack on Sunday night. Not sure if people saw it when I posted it, so please go check announcements and take a look at that. So it's about a 10-page Google Doc full of questions that you can use to study for the final. Hopefully it'll be a useful study guide. My suggestion for how to use it is to take it, make a copy, and try to answer the questions on your own or with a group of friends. If there's anything that you're completely stumped by, mark it with a question mark, and then bring it to class on Friday. And we're going to have a final exam review session and AMA on Friday. So bring questions about anything on that list of questions that stumps you, and we'll talk about it then. Other than that, we can talk about whatever you want on Friday. So it doesn't have to be even necessarily related to the course. You can ask me anything you want. So that's the plan for this Friday. Okay, I think we have Karissa back.
Hey.
Hi, Karissa.
Wow.
Yeah.
I'm tethering.
I'm glad you were able to rejoin us for the last couple of minutes. Yeah, so sounds like there's some technical difficulties on your end. I took the opportunity to talk about some logistical stuff for my class. So we only have 2 minutes officially left in class. I'm sorry that the end of your talk got cut off, but that was amazing. Thank you so much for a wonderful presentation.
Thank you.
And if you want, I can share the slides with my class, if that's okay with you. I also shared the link to descent patterns. So decent as in decent, and also as in decentralized, I suppose. Decent patterns.xyz is where Chris's handbook on building decentralized systems, or the handbook that she's working on along with a bunch of other cool people. That's where it will be posted eventually.
It will be posted eventually, yes.
Okay. Yeah.
And
any
I can
other,
also share
any other resources that you want to share?
Totally. I'll share links, and people can get involved. I'd really love to help anyone. If you want to also reach out on Twitter, follow me on Twitter. OK Distributes my handle. I post a lot of fun stuff related to peer-to-peer applications and practical stuff as well. And if you want to get involved, reach out and talk. I'm on IRC. You can get involved. It's all open source.
Thank you so much, Karissa. All right.
Yeah,
All right, let's, so sorry about the technical difficulties. Man, I thought we had everything working well this time, and it almost worked.
it's my internet. I don't know. Yeah.
Yeah, sometimes it's unavoidable.
Totally bored.
Okay. All right. Take care, everybody.
Thanks.
Have a good next couple days, and I will see you on Friday. Bye.